welcome to the deep dive. If you're prepping for the GCFA, that's the GIAC Certified Forensic Analyst, or just need a solid refresher on key digital artifacts, you already know this field needs almost surgical precision.
Absolutely.
Today we're diving into a bunch of critical forensic scenarios. We'll look at exactly which artifacts you need to crack them.
Yeah, think of this deep dive as sort of an intense knowledge workout. We're moving fast, from baseline system activity right through to complex stuff like memory forensics. And the goal isn't just getting the right answer. It's really about digging into the why. Why this event ID is the smoking gun, or why that timestamp anomaly is where you focus first.
Exactly. It's like a shortcut to boosting your correlation skills across those four big GCFA areas: baseline activity, timelines, volatile artifacts, and IR strategy. So here's how it works. We'll lay out a scenario, give you some options, and then we'll break down the forensic side of it in detail. Ready to jump in?
Let's do it.
Okay, first up, the absolute foundation of any investigation: telling normal system and user activity apart from those first signs of malicious behavior. We'll use standard Windows artifacts here. Hashtag tagged 1.1. Deep dive on logon types. Scenario 1, normal activity. All right, imagine you're looking at a Windows security event log. You see event ID 464 logon type to account name.jdo. Wait, which activity fits this best for normal user behavior? Is it A, remote desktop session, B, interactive logon at the local machine, C, scheduled task execution, or D, network logon from a remote machine?
Okay, the answer here is fundamentally B, interactive logon at the local machine. And honestly, this logon type 2, it's maybe the single most critical number to know in Windows forensics.
Why is that? Why so credible?
Because type 2 always means someone physically sat down at that machine's keyboard and logged in directly at the console.
Okay, but couldn't an attacker compromise the machine and then log in locally? Does it rule that out?
Well, no, it doesn't rule it out completely, but type 2 gives us a really strong baseline. Think about it. If the machine's in New York and you see a type 2 logon at 3 a.m. local time,
Okay.
that's immediately suspicious physical access, right?
Makes sense.
And maybe more importantly, seeing type 2 helps us differentiate from common lateral movement techniques. We know it wasn't type 10, which is RDP or remote interactive, and it wasn't type 3, which is a network logon, like accessing file shares or network services. So when you see type 2 and there's no source network address listed in the event, you can be pretty confident the access wasn't remote or network-based initially.
Got it. That context is key. Scenario 2, prefetch. Okay, moving on. You're analyzing a prefetch file for an app that ran. What piece of info should you focus on first to figure out normal usage patterns? A, last execution time, B, application size, C, number of executions, or D, file path?
Well, if you're trying to establish what's normal versus abnormal behavior, you really need to measure frequency, right? So the key metric here has got to be C, number of executions. The last runtime, option A, that's critical for placing it on a timeline, definitely. But it's the count that tells you about the behavior itself.
How so?
Think about a utility that normally runs, say, once a week. If suddenly your prefetch data shows it running 100 times in an hour, that's a massive behavioral shift. It screams automation, maybe a script stuck in a loop, or something malicious.
And just a quick technical reminder for everyone. Prefetch files, you find them in %systemroot %prefetch. Windows Memory Manager uses them to speed up app launches.
Exactly.
So they confirm an app ran, and crucially, they list the files and directories the app touched in those first 10 seconds of launch. That can reveal stuff like hidden file paths or weird resource access.
Precisely. And don't just look at the execution count. You need to dig into the file itself, look at the directories listed inside. If notepad.exe, for example, suddenly shows dependencies linking to some non-standard temp folder, well, that suggests it was used in a really unusual, maybe malicious way.
Good point. Context matters there too. Scenario 3, auto start. All right, check out this registry entry. HKCU software Microsoft Windows current version run. And the value is just Skype. What does this suggest about normal user activity? A, Skype is set to run at startup. B, Skype is installed in a weird place. C, Skype was recently uninstalled. Or D, Skype is scheduled for an update.
This one's pretty straightforward. The answer is A, Skype is set to run at startup. That whole run key path, it's a classic persistence mechanism.
Right.
For perfectly normal user-facing apps like Skype or Teams or whatever, seeing an entry here is incredibly common, but the forensic angle is crucial. Any program listed here gets executed every single time that specific user logs in.
So when we're investigating a system, this is a hotspot, whether we're hunting for legit apps or malware persistence. What's the difference between this HKCU path and the HKLM equivalent? Is that important?
Oh, absolutely vital, especially for scoping containment. So HKCU stands for H key current user. Any persistence set here only affects the specific user profile tied to that registry hive. So if you find malware persistence in HKCU, run. Only that one user is impacted when they log in. But if you find it in the equivalent path under HKLM, that's H key Y local machine, that malware is going to execute for every single user who logs onto that system. Much wider impact.
Ah, got it. So HKLM is system-wide. HKCU is user-specific. Big difference in an incident. Hashtag 1.2. Deep dive on malicious activity indicators.
Okay, let's pivot a bit. We've talked baseline normality. Now let's look for those indicators of compromise, the IOCs.
Right, the red flags.
Scenario 4, infection vector. Time to correlate some artifacts. You find a shim cache entry for malware.exe. You also see a registry run key pointing to malware.exe. And then, boom, event ID 4720 indicating a new user account was created. What's the most likely initial infection vector here? A, malicious email attachment. B, drive-by download. C, USB stick infection. Or D, RDP compromise.
Okay, let's connect the dots. We have execution evidence from shim cache, immediate persistence set up via the run key.
Yeah. And then, critically, that event ID 4720 new user account created, this sequence run, persist, create backdoor account, it strongly points towards a malicious email attachment. It's really characteristic of a payload being dropped, often from phishing or malicious email, and then executed to establish a foothold.
You called that 4720 event the smoking gun.
No.
Why is that ID so critical in this sequence?
Because it signals the attacker successfully finished phase 1 of post-exploitation. It's not just that the malware ran, it means it likely escalated privileges and is now actively setting up long-term access.
Ah, okay.
Creating a new account with 4720, or maybe adding an existing user to a privileged group like administrators, which is event ID 4732, that tells you the attacker moved beyond just getting in. They're establishing a solid foothold. When you see that, you know the compromise is likely pretty deep.
That makes sense. It's a milestone for the attacker. Scenario 5, malicious logon. All right, back to logons. Event ID 4624, so a successful logon. Logon type. 3, account name JWE, workstation name WS01. What does this tell us? A, interactive logon from WS01. B, RDP session started. C, network logon to access shared resources, or D, scheduled task ran.
We're back to the logon types again. Type 3 specifically means C network logon to access shared resources. This typically happens when a process or a user account on one machine, WS01 in this case, authenticates to access something on the target machine. Could be a file share, a printer, maybe some network service.
Okay, so this can be perfectly normal network activity, right? But it's also a favored tool for attackers moving laterally.
Absolutely. It's huge for lateral movement. Or once attackers compromise initial credentials, they often use tools that trigger Type 3 logons, think PSExec, or even just standard file copying across the network using NetUse or mapped drives.
Why Type 3 specifically?
Well, it's generally less noisy or obvious than an interactive logon, Type 2 or Type 10. Plus, it's necessary for many remote administration and file sharing protocols. So if you see a Type 3 logon coming from a workstation, like WS01, that has absolutely no business connecting to this particular server or resource, that's immediately where you pivot your investigation for lateral movement. It often signals credential reuse across the network.
Gotcha. So monitor those Type 3s, especially from unexpected sources. Hashtag personalized study and focus practice. Okay, quick pause. We just blasted through 5 key artifacts covering user baseline and initial compromise signs. Now, if distinguishing between logon Type 2, Type 3, and Type 10 still make you hesitate, or you weren't instantly sure about the 4720 event, that's okay. You've just pinpointed a potential weak spot. Totally normal for anyone prepping for the GCFA.
Yeah, the complexity here isn't just knowing the artifact names, it's memorizing and instantly recalling literally thousands of specific values, flags, event IDs. It gets overwhelming, and that's where just reading notes or generic practice falls short. You need targeted practice. This is exactly where tools like FlashGenius really shine. They use AI-guided learning paths. So instead of you guessing what to study or wasting time on stuff you already know cold, the system identifies precisely where you struggled. Maybe it was the logon types, or perhaps the difference between shim cache and am cache.
Right.
And then it gives you unlimited practice questions specifically focused on those weak areas across all the GCFA domains until you master them. It makes your study time much more efficient.
It's about using AI to get that surgical precision we mentioned earlier.
Yeah.
You need to see 4720 and instantly think new user account created, not wait for the multiple choice options. That speed is crucial both for the exam and, frankly, in a real incident response scenario.
Couldn't agree more.
Okay, let's shift gears. We're moving into the file system itself now, NTFS timeline reconstruction. This is all about reading the MFT, the USN journal, interpreting timestamps to figure out exactly what happened to files and when. Hashtag 2.1, deep dive on MFT timestamps. Scenario 6, MFT activity 1. Okay, imagine an MFT entry shows these timestamps. Creation time, 10.15.30, modified time, 10.12.00, access time, 10.25.00. What can you deduce just from that? A, the file was deleted after access. B, it was modified but not accessed. C, it was accessed but not modified. Or D, it was modified after creation.
This one's about simple chronological order. The modification time, 10.2 and 12.00, comes after the creation time of 10.15.30.
Right.
So the straightforward answer is D, the file was modified after creation. This tells us the basic sequence: file created, then contents changed 5 minutes later, then access 5 minutes after that.
Okay, makes sense.
It establishes the baseline life cycle for that file within that window.
Scenario 7, MFT activity 2. Similar idea, different times. MFT entry, created on 9/15, modified on 9/20, accessed on 9/21. What can you conclude about this file? Let's say it's called notes.txt. A, notes.txt was deleted. B, notes.txt was modified after access. C, notes.txt was accessed after modification. Or D, notes.txt was never accessed.
Again, just follow the sequence. The latest timestamp here is the access time, 9/21. That happened after the modification time on 9/20.
Okay.
So the conclusion is C, notes.txt was accessed after modification. This sequence might suggest, a user edited the file, saved it on the 20th, and then maybe opened it again on the 21st, possibly just to read it over.
Right.
It's worth remembering, though, that MFT access time tracking, it's often disabled by default in modern Windows versions to save on performance overhead.
Ah, good point.
But when it's enabled and present, that access timestamp is a really powerful piece of data.
Scenario 8, MFT anomaly. Okay, this is a classic. You find an NTFS file where the last modified timestamp is actually earlier than its creation timestamp. What's the most likely reason for this weirdness? A, the file was copied from somewhere else. B, it was opened and closed without changes. C, the system clock was wrong. Or D, a backup application accessed it.
Yeah, this is a big one for forensic analysts. The most common explanation by far is A, the file was copied from another location. And to really get why, you have to understand there are actually two main sets of timestamps within NTFS metadata for a file.
Okay, wait. Two sets. Let's break that down. What are they?
You've got the timestamp stored in the standard information attribute, often called $6. These generally reflect the original timestamps of the file when it was truly first created, last modified, or last accessed on its source volume, perhaps.
Okay, SI holds the original times. What's the other set?
The other key set is in the file name attribute, or $5. Now, the timestamps in the $5 attribute, the operating system updates these every time a file gets a new MFT record entry, like when it's copied to a new location on the same volume, or more commonly, moved or copied between different NTFS volumes.
Ah, okay. So how does that cause the anomaly?
When you copy a file, Windows usually creates a new MFT entry at the destination. The 5N creation time gets updated to the current time of the copy operation. However, the SIGSUP modified time often gets preserved from the original source file.
Got it.
So you end up with a situation where the 5N creation time, time of copy, is newer than the inherited $SIGSUP modified time, original modification time. That's your paradox. Modified time appears older than creation time.
That makes perfect sense now. So if I see that anomaly, the first thing I should suspect is a copy or move operation.
Exactly. That's your primary hypothesis.
But couldn't an attacker use something like time stomping? Deliberately change the timestamps to confuse an analyst? Could they create the same effect?
They absolutely could try. Time stomping usually targets the CSI dollar timestamps, so an attacker might push back the CSI on modified time. But here's where you need to look deeper. You check the MFT record change time as well.
Okay.
Even if they stomp the CSI dollar times, modifying that attribute usually updates the MFT record change time to the current time of the manipulation. So if you see that classic modified before created anomaly plus a very recent MFT record change time, that's a huge red flag suggesting intentional tampering, not just a simple file copy.
Nice. Look for that secondary indicator.
Always correlate.
Scenario 9, file access time. Simple question, maybe. When you're analyzing an NTFS volume, which artifact is the most direct source for finding the last access time of a specific file? A, the MFT entry. B, shim cache data. C, registry last write time, or D, a prefetch file?
Well, for that specific piece of metadata, the last access time, the most reliable and dedicated source is A, the MFT entry itself, specifically the last access time field within the MFT record for that file. While other things like shimcache or prefetch might imply access because they track execution, the MFT entry contains the direct timestamp recorded for the file simply being opened or read, assuming access time tracking is enabled, of course.
Scenario 10, NTFS artifact. Similar vein. In NTFS, which artifact would you check first to find out the last time a file was specifically opened? A, MFT access timestamp, B, the USN journal, C, a prefetch file, or D, a registry run key?
Yeah, this really just reinforces the point. The primary artifact designed to record that specific event opening or accessing is the AMFT access timestamp. The USN journal tracks all sorts of changes. Prefetch tracks initial execution. Run keys are for persistence. But for the simple act of opening, the MFT access time is the designated attribute. Hashtag tag 2.2, deep dive on USN journal and timelines.
Okay, let's move from the somewhat static NFT picture to something more dynamic. The USN journal.
Right, the update sequence number journal or change journal. Very useful.
Scenario 11, USN journal reason. You're looking at a USN journal entry. It has these reason codes. File create and also data overwrite. The timestamp is March 5th, 2023, 9:30 a.m. What can you infer happened at that exact moment? A, the file was deleted. B, it was created and then modified. C, it was moved. Or D, it was just accessed for reading.
The real power of the USN journal comes from these granular reason codes. This entry explicitly lists both file create and data overwrite. That combination directly tells us the file was created and then modified, essentially popped into existence, and then its contents were immediately changed or overwritten right at 9.30:000.
What kind of activity causes that?
Oh, lots of things. Software installation routines often do this, create a config file, then immediately write settings to it.
Yeah.
But in a malicious context, think about a malware downloader dropping a payload file create, and then immediately unpacking the real malware into that same file, data overwrite. It's a common pattern.
So you said the USN journal is more dynamic. It sounds like it gives us the action movie version of the file's life, while the MFT gives us the final snapshot. Is that a fair way to put it?
That's a great analogy, actually. Yeah, the USN journal, or change journal, it tracks pretty much every significant file system operation as it happens. Creation, data writes, attribute changes, renames, even deletions, things that might not always update every single MFT timestamp immediately.
Okay.
So for an analyst, it's incredibly valuable for filling in the gaps between the MFT timestamps, especially when you're trying to trace really rapid file changes like a script running or malware deploying itself. It gives you that blow-by-blow sequence.
Scenario 12, sequential timeline. All right, imagine you're building a timeline from various artifacts, MFT, USN journal, logs, etc. You notice a whole cluster of entries, maybe file creations or modifications, all with timestamps that are sequential and packed really close together, like within seconds or even fractions of a second.
Yeah.
What does that pattern usually indicate? A user manually copying a bunch of files. B, an automated script running. C, a system crash recovery process. Or D, just a typical user login session.
Yeah, that rapid fire sequence. Humans, even if they're clicking fast or dragging and dropping quickly, generally can't generate events that are perfectly sequential down to the second or sub-second level consistently.
Right, there's always a bit of unevenness.
Exactly. That kind of machine-like precision, that rapid sequential burst of activity, it's almost always the sign of non-human action. So the most likely answer is B, an automated script executing.
Could be benign or malicious then.
Could be either. Might be a totally normal scheduled backup script kicking off. Could be a system process doing routine work. Or it could absolutely be an attacker's deployment script, setting up persistence, driping tools, modifying configurations all in one go. The key takeaway is that the source of the activity is likely automated, so your investigation should pivot towards finding the script or process that launched it rather than assuming direct user interaction. Hashtag simulating the exam experience. Okay, we hit some really complex stuff there. MFT attribute inheritance, those USN journal reason codes. To really get this level of correlation down cold, you can't just understand it passively. You need to practice applying it, ideally under some pressure, like you'd face in a real investigation or obviously on the GCFA exam itself.
Yeah, absolutely. And this is where just flipping through flashcards kind of falls short, right? You need to simulate the real thing. That's where tools like FlashGenius are so helpful here. They offer real exam simulations. They're designed to feel like the actual GCFA test environment. You get the timed conditions, the same types of scenario-based questions that force you to correlate multiple artifacts, not just recall definitions.
And just as importantly, maybe even more so, is what happens after the simulation. Their AI-powered smart review feature. It doesn't just tell you if you got questions right or wrong, it actually analyzes where you struggled.
How does that work?
Let's say you consistently missed questions involving MFT and USN journal correlation. The AI picks up on that pattern. Then, the Smart Review gives you targeted explanations focusing specifically on how those two artifacts interact, why one timestamp matters more in a certain context, etc. It effectively turns every mistake you make into a concrete learning opportunity. That's probably the most efficient way to prepare for a high-stakes exam like the GCFA.
It really is the difference between just blindly reviewing a massive textbook and having like an AI tutor guiding your study sessions, making sure you shore up your actual weaknesses instead of just rereading stuff you already know.
Exactly. Focused, efficient practice.
All right, let's dive into volatile data now. We're focusing on those crucial event logs and execution artifacts, things like prefetch, shimcache, amcache, that can show us what an attacker did either in real time or immediately after running something. Hashtag TagCheck 3.1, deep dive on key Windows event IDs, scenario 13, an initial access vector. Correlation time again. You see event ID 1102, that's the security log being cleared. Right around the same time, you see a flurry of event ID 4625's failed logins, all with logon type 3, the network logon. What's the most likely initial access vector based on this combo? A, phishing email, B, brute force attack, C, malicious USB, or D, drive-by download.
Okay, the sequence is really the key here. You've got numerous failed network logins. That's 4625 with type 3. That pattern itself is textbook brute force or maybe password spraying against network services.
Right.
Then, immediately following that activity, you see event ID 1102, the log clearing event. That's the attacker trying to cover their tracks, erasing the evidence of all those failed attempts. So this specific combination points very strongly towards B, brute force attack. They hammer away until they get in, then immediately try to wipe the slate clean.
What if the 1102 event, the log clearing, happened before the failed logins? Would that change how you interpret it?
Oh, definitely. If the log was cleared first, that suggests a different motive. Maybe someone trying to mask an impending system failure, or perhaps just routine admin cleanup before starting a noisy process. It's less indicative of an attacker covering intrusion tracks. But when 1102 comes after a string of 4625s, and presumably after a successful 4624 logon, which must have occurred in between, then yeah, it's almost always an attacker trying to hide their entry point.
Makes sense. Sequence matters.
Critical.
Scenario 14, process investigation. Okay, you've identified a suspicious executable running. You need to figure out what launched it. Which artifact is going to be the most helpful for identifying the parent process? A, Windows event logs. B, prefetch file. C, shimcache. Or D, amcache.
Right, so options B, C, and D, prefetch, shimcache, amcache. They're great for confirming that the executable ran and maybe when, but they don't inherently record the parent-child process relationship.
Okay.
The definitive source for tracking that process hierarchy is A, Windows event logs. Specifically, you need to look for event ID 4688. This event logs new process creation, but crucially, if you have the right auditing policies enabled.
Big if sometimes.
Big if, absolutely. But if it's enabled, 4688 will record the creator process name and the creator process ID. That gives you the direct link back to the parent process that spawned the suspicious one.
And knowing the parent is everything, isn't it? Like if malware.exe was launched by explorer.exe, that suggests maybe a user double-clicked it. But if it was launched by, say, PowerShell.exe or WinWord.exe.
Exactly. That tells a completely different story. Launched by PowerShell could mean a script attack. Launched by Word points towards a malicious macro in a document. That parental context from 4688 is what helps you determine the actual infection vector and guides your whole containment strategy. Without it, you just know a file ran. With it, you know how it ran.
Critical difference.
Huge.
Scenario 15, successful login. A quick knowledge check here. An analyst sees a bunch of failed logins, then finally a successful one. Which event ID number specifically indicates the successful login? A, 4625, B, 4624, C, 4768, or D, 477771.
Another one you just got to know. The definitive event ID for successful login event is B, 4624.
And 4625 is the corresponding failure.
Exactly. 4624 for success, 4625 for failure. Those are the two main logon events to always filter for first in the security log.
Got it. 4624 success, 4625 failure. Scenario 16, shutdown event. Okay, slightly different event type. Which event ID would you look for first to confirm that a system shutdown was specifically user-initiated? Like if someone clicked shutdown, A, event ID 10074, B, event ID 6006, C, event ID 4625, or D, event ID 1102.
To confirm it was user action, you want A, event ID GCFA. This event is logged in the system log, and it explicitly records when a shutdown or restart was initiated, and it usually includes which user initiated it and often a reason code they might have entered.
Okay, so what about 6006? I see that mentioned sometimes with shutdowns.
Right. Event ID 6006 just indicates that the event log service itself stopped. That happens during any shutdown, whether it was planned, user-initiated, or an unexpected crash. So 6006 confirms a shutdown happened, but 1074 tells you why, specifically if a user kicked it off.
Gotcha. 1074 for the user trigger. Hashtag 3.2. Deep dive on execution artifacts. All right, let's dive into those key execution caches. Prefetch, shim cache, and am cache. They all track execution, but in different ways.
Yeah, subtle but important differences.
Scenario 17, first execution. Which of these Windows artifacts would you prioritize if your goal is to determine the absolute first execution time of a specific application on the system? A, prefetch files, B, shim cache, C, am cache, or D, event logs, like 4688.
Okay, so while all four can potentially give you execution timestamps, the artifact that's generally considered the most reliable and often most granular for finding the true first execution time is C, amcache.
Amcache, why that one specifically?
Amcache data is stored in a registry Hive file, usually amcache.hvv. It tracks application compatibility information, but crucially, it often records a dedicated timestamp for when an application was first run, along with its path and file hash. Prefetch gives you run counts and last run time. Shimcache often just gives you the last modification time of the file. But amcache frequently nails that initial execution time, really valuable for pinpointing the start of an infection.
Okay, amcache for first execution. Good to know. Scenario 18, network correlation. Let's say you see a huge unexpected spike in network activity coming from a specific endpoint. Which Windows artifact should you check first to try and directly correlate that network spike with a specific process that might be causing it? A, event logs, B, prefetch files, C, SRUM, or D, registry hives.
Right. You need something designed to link process execution directly to resource consumption, including network usage. That artifact is C, SRUM, which stands for System Resource Usage Monitor.
That's SRUM. Okay, tell us more about that. Why is it better than just looking at network logs?
Well, network traffic logs, like from a firewall or NetFlow, show you the communication happening between hosts. But SWEM data, which is stored locally on the endpoint in the sredb.dat database, it tells you which process on that endpoint was responsible for sending or receiving network data, how much data it transferred, bytes sent or received, and over what time period.
So it connects the process directly to the network usage on the box itself.
Exactly. An analyst can parse the SRUM database and basically create a timeline showing, okay, this process, evil.exe, suddenly started sending gigabytes of data outbound between 2 a.m. and 3 a.m. It directly correlates the process with the network activity, making it ideal for spotting things like data exfiltration tools or malware beaconing heavily. It provides that crucial process context right there on the endpoint.
Very powerful for identifying the culprit behind suspicious traffic. Hashtags tag specialized tools and resources mastery.
You know, understanding these execution artifacts, amcache, shimcache, aram, it's not just about knowing the definition. For the GCFA, you need instant recall of where they live, what kind of data they hold, the format.
Yeah, it's a lot to keep straight. All the acronyms, the event IDs, the file paths, the volatility command syntax we're about to get into, it can feel pretty overwhelming. And if you do feel that way, remember that tools like FlashGenius aim to be more than just practice quizzes. They position themselves as a one-stop study resource hub. So beyond the practice questions, they also offer things like comprehensive study guides and quick reference GCFA cheat sheets. Those cheat sheets are perfect for when you just need to quickly look up, say, the exact fields in an event ID 4688 record, or remember the syntax for a specific volatility plugin, especially when you're under pressure either in the exam or during a real investigation.
Yeah, that quick, accurate reference is gold. In a high-stress situation, you don't want to be fumbling through notes. Having a reliable synthesized resource that gives you the critical details on SRUM structure or VAD anomalies or the $6 versus 5N timestamp differences, it saves incredibly valuable time and helps make sure you don't miss that one crucial piece of evidence.
Right. Reduces the mental load a bit. Okay, time for our final section. We're zooming out a bit to incident response prioritization in an enterprise context, and then diving deep into probably the most volatile data of all. System memory, using tools like volatility. Hashtag tagged, tag 4.1. Deep dive on IR prioritization and strategy. Scenario 19, containment priority. All right, you've detected a highly suspicious process running on a critical server. you need to prioritize immediate containment actions. Which artifact is the most critical to examine or capture first to inform those actions? A. Shim cache, B. AM cache, C. A memory dump, or D. The SRAM database.
Okay, containment is about stopping the bleeding now. To do that effectively, you need real-time information about the threat's current state, especially its